This conference will now be recorded.
I pressed the record button, unlike last time. Sorry for that. Okay, good. So last time I told you about branching processes and the Galton-Watson model. Today I want to talk to you about Hawkes processes. I'll give you an introduction to network theory, speaking about Erdős-Renyi networks, which in a sense are very close to the Galton-Watson process that I talked about, and I'll expand on that. And also the very famous by now, what people call scale-free networks. And then I'll talk about the giant components in these networks and their resilience. And this has a lot to do with the efficiency of vaccination campaigns and all these interesting topics. Okay, so let me talk about Hawkes processes, and I'll start by reminding you what Poisson processes are. So a Poisson process is a sequence of events, okay? And this is the time axis, and Poisson processes are events that occur at random times. So what does it really mean? It means that if you introduce a count of the number of events that happen up to time t, then each time something happens, this n of t increase by 1, okay? So you just count the number of events that occurred, and you have something like this, where each jump occurs at where one of these events takes place. And so the randomness is defined by the fact that the probability that dn is equal to 1 is equal to, at time t, is equal to lambda dt, where lambda is called the rate of the Poisson process. Okay? So this is very simple. I mean, things happen at random, and on every little time interval dt, there's a probability lambda dt for something to happen. And of course, the probability that nothing happens is 1 minus lambda dt. Okay? So it's a very well-known object, and I'm sure many of you have seen it on many occasions. So let me remind you a few basic properties of this Poisson process. So for example, you can ask, well, I'm giving myself a time interval capital T, okay? And the question I'm asking is, what is the probability P of n knowing T that I observed exactly n events in this interval of length capital T, okay? So in this particular case, I observe 6 events, but more generally, I can ask the question, and it's a little exercise for you if you want to derive it, but it's very easy to show that this is given by what's called a Poisson distribution. So it's lambda t to the n, exponential of minus lambda t, capital T, divided by factorial n, okay? So this is just a consequence of the definition of the Poisson process. There's no correlation whatsoever between events, and therefore you get this. So for example, and I've said that already several times before, the average value of n is lambda capital T. This is pretty intuitive. If lambda is the rate of events per unit time, so if you want, this is the units is second minus 1, then in an interval of time of length capital T, they are on average lambda t events. And another property of Poisson processes is that the variance is equal to the mean. So average value of n squared minus the average value of n squared is also lambda t, not squared, lambda t. And so this leads to the introduction of a quantity that's quite interesting to consider, in particular for practical application, which is what I'm going to call the clustering ratio. Rho, and I'm going to define the clustering ratio by the ratio of the variance over the mean. And of course, I'm going to go too far, so let me move my camera already. And from what I just said, for a Poisson process, this is equal to 1. Okay? Another interesting quantity that one can compute for Poisson processes is the insert time distribution. So if I call S the difference between two consecutive events, then it's easy again to show that P of S, the probability to observe a certain interval between two consecutive events, is a Laplace distribution, lambda exponential minus lambda S. Okay, so these are my basic observations about Poisson processes. Shouldn't go too high. And I'm going to tell you about various objects that are not Poisson processes and that need something different to be modeled with. Sorry, I'm trying to find the right height. Okay. Down a little bit. So let me give an example of something that actually has a clustering ratio less than 1, and examples of things that have a clustering ratio larger than 1. So intuitively, clustering ratio less than 1 means that the fluctuations are smaller than you would expect for a Poisson process, okay? So the way these events occur tend to be more regular than for a Poisson process. Imagine, for example, that you have a perfectly regular set of events. So these events occur not randomly, but like every second exactly. Then for a very large T, very large capital T, there would be no fluctuations at all in the number of events. And so the clustering ratio would be less than 1. So clustering less than 1 means that there's some kind of repulsion between events. Or if you prefer, anti-correlation. So if something happens now, it's less likely that something is going to happen just after that. And a very well-known example of a set of points that follows a repulsion type of process is the set of eigenvalues of a random matrix. So if you take a large random matrix and you diagonalize this random matrix, you can plot the eigenvalues, like in quantum mechanics. And if I plot the eigenvalues of a random matrix, I will find something that's much more regular than the Poisson process. And this is called level repulsion. And there's a long story about this in the nuclear physics literature first. This was introduced by Wigner. And of course, all the massive development of random matrix theory in the last 50 years, a lot of that is about the precise description of the set of points. So I won't go much into details, but that's an example of clustering ratio less than 1. And of course, taking the opposite of what I just said, if you have a clustering ratio greater than 1, it means that fluctuations are larger than for a Poisson process. And this means that you have what's called clustering. So on the contrary, there are correlations between events. If something happens, it's more likely than for a Poisson process that something else happens very soon after. And because of that, you will have bursts of activity and then activity that's lower in such a way that the fluctuations of this of the number of events in a time interval is greater than 1. Okay. And so if you do this very simple test for several time series, you realize that a lot of time series that we are interested in these lectures actually show some clustering properties. So for example, I told you about earthquakes. And if you look at the time series of earthquakes, then there's clear clustering. I mean, it's what people call aftershocks, for example. So we know that once an earthquake has happened, somehow the crust, the crust of the earth is fragilized, and this leads to a higher probability to observe more earthquakes. And in what I'm going to talk to you about today, Hawkes processes, actually, they were introduced by Mr. Hawkes in '72. And it was in the context of earthquakes dynamics. So it is fair to associate, as an example of clustering time series, earthquakes as the primary ones. But I told you about financial markets. Financial markets is also a prime example of clustering of activity. So for example, the activity in the financial market is every time the price of a stock changes, for example, you can put a mark when the price changes. And of course, this the mean value of the activity rate, the lambda, has increased over the years because, as you know now, people trade at a higher frequency. So lambda itself has increased. But apart from this increase of activity, one sees something that has always been the case before high frequency trading, before the electronization of markets. And since then, that hasn't changed, is the fact that when the price changes, it's actually more probable that the price is going to change again very soon after. And so you have this very, very strong clustering. I'm going to go back to that later. In social sciences, there's a very interesting story as well, and Hawkes processes are used to model earthquake, financial markets, and some social sciences phenomena. So for example, a case that's been studied empirically is the case of riots. So when you see the way the dynamics of riots take place, it is clear that there is also, as in earthquakes in a sense, the fact that when a riot has occurred, then in the nearby city, another riot tends to happen very close after. And this was actually studied in detail in the case of what happened in France in 2005. There was a wave of riots, some of you may remember, in the suburbs of Paris. And there is a very strong signal of clustering of these events. Okay, so a lot of example of clustering, starting from earthquakes, and this has led Hawkes to provide a model, a simple model for these clustering events that are now known these models as Hawkes processes. So Hawkes processes are also called subordinated in a way that I'm going to define, subordinated Poisson processes. So what does that mean? Well, it simply means that the Poisson process that I've considered up to now had a fixed rate of events, lambda. Now I'm going to imagine that this Poisson process has a time-varying rate of events. So the probability that dNt is equal to 1 is equal to lambda t dt, okay, where lambda t is now time-dependent. And the way it's time-dependent is going to depend on what happened in the past. So what Hawkes postulates is that lambda t is equal to some base rate value mu, which is going to be constant, plus the sum over all past events. So I'm going to write Tj is the time at which the jth event happened. And so it's the sum over all j's such that Tj is less than t of a certain kernel k of t minus Tj. And k is the Hawkes kernel as a function of the lag tau between the event that happened in the past and now. This kernel k of tau is a certain decaying function. For example, exponential. So for example, I'm going to take just after that a specific example where k of tau is exponential of minus alpha tau. But it could be something else. So what it means is that you're very affected by events that just happened, which increase the probability of having something happening again. But far away events, so when t minus tj becomes, in this case, much larger than 1 over alpha, then you tend to forget these past events, okay? So this is, if you want, what people, it's called an influence kernel as well, which means to insist on the fact that it's the influence of past events on the current level of activity. And mu is a baseline level. Okay? So there's another way to rewrite this equation, which in some cases is useful. So let me rewrite this as an identity as mu, the same, plus instead of having a discrete sum, I'm going to write this as an integral. It's integral from minus infinity to t of dnt prime k of t minus t prime. Okay, and you see it's the same because dnt prime, this is equal to 1 if something happened, if there's an event at t prime, and 0 if not. Okay. So let me give you a few properties of this model. The first property is what happens for the average rate of events in this model. So you see that lambda now is time dependent. So if I make a little drawing of lambda t as a function of t, then lambda t is going to look like this a little bit. Okay. And so you already see clustering by the eye, because there are moments where lambda is going to be larger. So many things will happen around these times. But I can define the average value of lambda across time. So that would be what I call lambda bar. Okay. This is the average level of activity when I average across time. So one can show that in certain conditions, this Hawkes process is ergodic, which means that I can think of lambda bar either as a time average or as an ensemble average, in the sense that you see that things are all random here, things happen at random. So lambda t is a random quantity. It's random because it depends on random events, and these random events are the underlying Poisson process. So you see why this is called the subordinated Poisson process. It's because conditional to lambda t is a Poisson process, but it is subordinated on another process, which in this case self-consistently depends on the process itself. Okay. So what happens if I try to compute the average value of lambda? Well, let me take the average of this equation here. And what I get on the left-hand side is lambda bar by definition. And on the right-hand side, I have mu plus, and here I'm going to use this expression. And in this expression, I'm going to note that the average value of dnt prime, this is equal to lambda bar tt prime. Well, tt. Okay. So what I get by taking the average of both sides of this equation is an equation where I get lambda bar in both sides of the equation. This is what I get. Okay. And so I'm going to give a name to this integral over t prime. So you see first that I can always change variables. I can always call t minus t prime tau, like I did in my drawing. And this integral over t prime from minus infinity to t of k of t minus t prime, this is also equal to lambda bar integral from 0 to infinity d tau k of tau. Okay. So let me rewrite this equation here. So what I get is lambda bar equals mu plus lambda bar times what I'm going to call R0. And of course, I'm not using this notation randomly, with R0, which is defined as the integral from 0 to infinity d tau of k of tau. And therefore, you see that lambda bar is equal to mu over 1 minus R0. Okay, well, if you see this expression, you see that it can only make sense if R0 is less than 1. Because otherwise you find a lambda bar which is negative, which doesn't make sense. And in this case, when R0 is greater than 1, it means that the feedback is so strong that actually the process diverges. There's no stationary state. Here, I've assumed ergodicity, as I've mentioned before, and this assumes that the process enters some kind of stationary state. But if R0 is larger than 1, then each event affects so strongly the future rate of events that the process kind of gets self-excited so much that it runs away to infinity. And actually, I've used a term that's often used in this context, which is self-excited process. So K of tau is the self-excitation feedback, which makes the system interesting, but potentially unstable. So if R0 is greater than 1, the Hawkes process is unstable. So there's a lot of things that one can do with these Hawkes processes. They're actually very, very nice from a mathematical point of view. You can compute all sorts of things exactly. For example, you can compute correlation functions. Here I've computed the average, but I can also compute correlation functions. And correlation functions are going to be needed if you want to measure the variance, because the variance is directly related to the 2-point correlation function of the process. So one can do that. One can actually very easily calibrate this process on data, and that's why it's very successful in the literature. There's a long list now of time series on which people have tried to fit Hawkes processes. And in particular, what's really interesting about the 2-point function is the clustering ratio, which is a summary of the 2-point functions, if you want. And in this case, it's actually, not completely trivial, but one can show, and I'm not showing here, so let me insist that it's not proven here. And those who are interested, I can give you some literature, but it's not completely trivial, actually, is that for Hawkes processes, rho is given by 1 over 1 minus R0 squared. So what's nice about this result is that, as you see, rho, this clustering ratio, is independent of mu and of K of tau, except from the norm of K of tau. So what I'm saying is that you don't care about the detailed shape of K of tau. The only thing you care about, except R0, of course. So once you know the norm of K, then you don't need to know anything else. You don't need to know mu either. So you don't need to know the underlying baseline level of activity. You can derive the value of R0 from the measurement of rho only. Okay, because for example, imagine that you say, but here maybe that's a way to measure R0. Well, it's not, because a priori you don't know what mu is. Okay, so what's nice about the clustering ratio is that all reference to the details of the Hawkes process, that is mu or the detailed shape of K, is actually disappears. So you can have an idea of the value of R0 just by looking at the clustering ratio. So let me give you two limits. One is the limit where R0 goes to 0. So what happens if R0 goes to 0? Well, you see that if R0 goes to 0, it means that somehow there's no feedback. And what we recover is the Poisson result, rho tends to 1. But what's more interesting is the case when R0 goes to 1. By the way, I haven't insisted on that, but clearly this formula shows that it's always greater or equal to 1, right? So there's always clustering in the Hawkes processes, which is what we wanted. We wanted to describe a clustering, a model with clustering. And let me come back to something I haven't said, I should have said before in a second, which is I'm assuming that K is strictly positive here. And if K is negative, then the model is not very well defined. So here I should have said that K is positive. So it's really something that describes self-excitation and not self-inhibition. So when R0 goes to 1, then you see from the formula that rho goes to infinity. And so what's surprising is that if you calibrate the Hawkes process to financial markets, you find that R0 is indeed very close to 1. And this is interesting because it means that somehow financial markets are extremely fragile. You see that R0 equal 1 again is the boundary between a stable process and an unstable process. If the process would be slightly more self-exciting, then it would be unstable. And for some reason, which is not completely clear even at this stage, financial markets, if you calibrate them with a Hawkes process, systematically gives you values of R0 which are close to 1, suggesting close to instability, that financial markets are poised at the verge of instability. So of course you could say, well, maybe it's because the Hawkes process is not a good model for financial markets, and that by calibrating a Hawkes model, which is not the right model, you get R0 close to 1, and that may well be, but I'm just pointing that out to you, which is a very interesting, I think, observation, is that when calibrated to financial markets, one finds a kind of incipient instability from the model, which goes actually hand in hand with many things I told you about financial markets already. It seems that there are power law distributions, crashes happen all the time. So maybe all this is related to some kind of intrinsic instability. Of financial markets. At least this is something that researchers are investigating now, is trying to understand whether or not there are good reasons for financial markets to be close to a critical point. Okay, so let me finish this chapter on Hawkes processes by giving you the example of K of tau exponential. So if I write K of tau equal R0 alpha exponential of minus alpha tau, then I've normalized it correctly in such a way that it starts at R0 alpha here, and the area is given by R0. Then let me give again the equation. Lambda t is mu plus integral up to t of dnt prime k of t minus t prime. And the exponential the exponential shape of k of tau has an interesting property, which is always the things that work well with exponential, is that if I take the derivative of this equation with respect to time, then d lambda t dt, then I'm not going to detail the calculation. It's easy enough to do. What you get is minus alpha lambda t minus mu. This comes from the derivative of k with respect to t, and using the fact that k is an exponential, which actually reproduces lambda t minus mu, and then plus R0 alpha dnt dt. And so what we know is that dnt is a conditional Poisson process. So dnt can be written as a deterministic part, which is related to the average value of dnt, which by definition is lambda t dt, plus a fluctuating part. And the fluctuating part, so if you think of this process in a kind of coarse-grained manner, you see that the average value of dnt conditioned to lambda t is lambda t dt, but there are fluctuations, and the fluctuations of a Poisson process are proportional to the rate of events. So the fluctuations can be written as psi, some noise, square root of lambda t dt. So here I'm cheating a little bit because this is not very rigorous what I'm writing. I mean, dnt is either 0 or 1. So in order to go from here to there, I'm kind of coarse-graining the system and applying a kind of central limit theorem to dnt. So you see, what I'm trying to give you here is not a mathematical proof, although everything that I'm going to say can be shown to be rigorous in some limits, but it's just an intuition about what's going on in this model. So what I'm saying is that this dnt dt is going to have an average value, lambda t, and fluctuation. And so if I follow this thing, at least naively, what you get is that there's a piece here of this guy which is going to add to this one, and a piece that's going to remain as a noise. So again, I'm not detailing the calculation, but what you get by regrouping terms is minus alpha 1 minus R0, lambda t minus lambda bar, where lambda bar is the lambda bar that I defined before. It's mu divided by 1 minus R0. So actually here, lambda bar times 1 minus R0 is just the mu guy that you had here. And the lambda t 1 minus R0 comes from this term plus the one coming from there, plus R0 alpha square root of lambda t times the noise, psi. A Langevin noise, let me call it eta. This is a Langevin noise. You remember Langevin noise are ill-defined. They're of order 1 over square root of dt. And this is what you would get from here. Dividing by dt gives you a noise that's 1 over square root of dt. So it's a Langevin noise. Okay, so that's where I wanted to arrive at, because what you see is that you have a differential equation which is such that there's an average. So what does this stochastic differential equation mean? It means that lambda t is fluctuating around lambda bar. You see this is a mean reversion term. This is a kind of harmonic oscillator term, which pulls lambda t back to its average value. So we already know that. We already know that lambda t fluctuates around an average value lambda t. But the strength of the reversion is decreased as R0 approaches 1. So if you want to see it simply, you see that alpha 1 minus R0 is the time scale of the mean reversion. You see dimensionally, alpha 1 minus R0 is the frequency. And so this is the relaxation time, or the inverse relaxation time. And the inverse relaxation time is 1 over alpha 1 minus R0. So this is, if I write here in a corner something that, if I write a harmonic oscillator, d lambda t equals minus omega lambda t minus lambda bar plus noise. This is also called the Ornstein-Uhlenbeck process. Then one knows that 1 over omega is the characteristic time scale of the relaxation of such a process. You can show it very easily. So what plays the role of omega here is alpha 1 minus R0. So I get the relaxation time that is 1 over alpha 1 minus R0. So what it means is that when R0 goes to 1, you have two things happening at the same time. You have that lambda bar diverges. So the process becomes more and more intense. But at the same time, the relaxation time of the process diverges as well. So relaxation time also. So this is a process, this is a phenomenon that's very usual in a statistical mechanics model, where the approach to a critical point, because R0 equal 1 is a critical point, is a point beyond which the model is unstable, then at the same time, there's something that diverges, which here is the average rate of events. So in a physical system, it's often, for example, the susceptibility of the system that diverges. And at the same time, the relaxation time, the speed at which the system relaxes to equilibrium also diverges. And that's what you see simply coming out of this equation. And that was not clear from the quantities I've told you about earlier. Here, one has, on top of these results on lambda bar and rho, one has a result on the relaxation time. So how this Hawkes processes evolve with time, really. And we see that close to criticality, they actually becomes very slow. So the other thing I wanted to tell you is that there's a very close analogy between Hawkes processes and the Galton-Watson branching process that I've told you about. One way to think about it is just looking at this equation here. And this equation, in a very precise mathematical way, can be shown to mean that there are ancestors arriving in the system at rate mu. And then these ancestors, they give rise to children. And they give rise to children exactly like in the Galton-Watson process. And so what you gain compared to the Galton-Watson process here is that you have some time dimension that allows you to know exactly when these children get born, if you want. But in terms of the structure of the families, it's everything that happens underlying this model is the same as what happens in the Galton-Watson process. And one way to realize that this is the case is looking at this equation again. And if you remember, I told you that the Galton-Watson process in the continuous time limit had a growth term proportional to R0 minus 1 lambda, which is what I wrote last time. I wrote something like R0 minus 1 n. So that was dn dt. And then a fluctuation term, which is proportional to square root of n. So I told you last time, this is the continuous time limit of the Galton-Watson process. And you see that it's very, very similar here. So it's just a hint that these two models are very closely related. I realize that there's something I didn't tell you to justify my mumble here about taking a coarse graining, making this bold interpretation of dn dt as a noise. Actually, it becomes more and more justified to do this as the process becomes slower and slower. So when R0 goes to 1, as I just said, the relaxation time goes to infinity. The system becomes slower and slower. And so it is possible to make a change of scale, to coarse grain the system if you want, and to actually think of this DNT as a Gaussian process in the limit, because the process is very slowly evolving. So on the time scale of the evolution of the process, I can aggregate many of these DNT, which are only 0 or 1, and by aggregating them, I get what I wrote here, which is a continuous time Gaussian process. So for those of you who are worried by my Cavalier way of handling this term, it's actually everything is well defined and justified in the limit when R0 goes to 1. And in that limit, the process is equivalent to a critical branching process. Okay, so let me leave Hawkes processes and go to networks now. The only thing I wanted to tell you before leaving them is that Hawkes processes can be generalized in many ways. So for example, you can have a multi-dimensional Hawkes process. You can add indices. You can have n processes happening simultaneously. So for example, imagine the activity of n different stocks in the stock market, and then you can add a vectorial and a matrix generalization of these Hawkes processes, saying that what happens on I is affected by what happened on J, mediated by an influence kernel that now becomes a matrix in the stock space and has some time dependence. So the whole artillery can be generalized to many cases, and this is one of the cases that's been considered in the literature. Okay. So Hawkes processes are important because they can be calibrated to data, and they're important because they are very closely related to branching processes. So now let me leave, or apparently leave, what I told you about branching processes, but you'll see that we'll soon recover them in another incarnation and go to network theory. So the reason people are very interested in networks is that there are networks everywhere around us, and they're extremely relevant in many situations. For example, electric grids are networks of cables and nodes, which are the places where electricity is produced. There's a physical example that you all know well, which is polymer gels. For example, the white of an egg is a liquid when the polymers are independent, but then when you heat the white of an egg, then these polymers attach to each other. They create a kind of network, and once the network is completed, the object is solid. It's not a liquid anymore, and this is related to the phenomenon of percolation, which I'm going to talk about. So in the case of the white of an egg, it's really interesting because one sees a transition that we'll comment later between a case where the network is made of disconnected clusters, and it's in the case of the egg, it's a liquid, and the case when there is a giant component where the network includes a very large number of different molecules, and in the physical sense, it's a solid. So social networks, of course, no need to speak about them. Social networks, whether they're virtual, like Facebook or other type of social network, or actual physical networks, networks created by contacts between people. And your social network, in the sense of who you meet every day, is of course extremely important in view of pandemic transmission and so on. But there are also economic networks like banking networks, who lends to whom, firm networks, who produces what. So that's called the input-output network. So some firms produce goods that are useful for other firms who themselves produce things. So there's a network of interaction between firms. There are ecological networks. So some species eat other species. So there's a predator-prey relation between species. And all these networks are crucial to understand emergent phenomena, because depending on the property of the underlying networks, you can have, in the case of COVID, for example, you can have either propagation across the whole population or only limited clusters of infection. And in the case of the white of an egg, as I said, you can either be in a liquid phase or in a solid phase. There are many, many other examples, like if you put conductors at random in space, you only have little islands of conductors that overall do not conduct electricity, or is there a giant component which allows the whole thing to become carrying electricity from one side to the other of the samples? So there's a huge incentive to understand the properties of networks in general. So a network is made of nodes. Okay, so I have nodes, and I have links or edges. Okay. So for example, this is a network that contains two clusters. So I'm going to use the terms edges or links to mean the same thing. And so you see here that an ensemble of nodes that are such that I can go from any one to any other one following edges is called a cluster. And the question is, do I have in my network a lot of small independent clusters, or do I have on top of small clusters, do I have a giant cluster, which in this case would be something like this, which involves maybe not all the nodes, but at least the finite fraction of all the nodes. So I will speak more about giant components later, but you have an intuitive feeling already at this level, is to know whether there is a cluster that covers a finite fraction of the number of nodes in the limit where this number goes to infinity, or if I only have, isolated guys. And of course, I can have a mixture of both things. For example, in this case, I would have a big cluster and an isolated cluster. But of course, this is hand waving, and one has to make more precise statements later on. Okay. So I'm going to give you two ways to construct these networks. One is the simplest and the oldest random construction of networks, which is called the Erdos-Renyi networks. And then I'll give you another type of construction, which leads to, in a sense, more interesting graphs, which are scale-free networks. Okay, so Erdos-Renyi network, how does that work? Well, so imagine that you have n nodes. I pick at random a pair of nodes, for example, this one and this one, ij. And for each of these possible pair, I decide that there is a link with probability p over n. and there is no link with probability 1 minus p over n. Okay? So this is my construction. It's all independent. Every link is independent. I mean, every potential link is independent, and it becomes filled with probability p over n, and it's left empty with probability 1 minus p over n. So you might ask, why do I put a p over n here? Well, it's because I want the model to remain well-defined in the limit when n goes to infinity. And if you think for 2 seconds, you realize that for each node, there are n minus 1 possible neighbors. And since each edge is present with probability p over n, the average degree, so the average number of neighbors, is given by p over n times n minus 1. So for large n, this is equal to p. So in this model, p is the average connectivity of the graph, or the average number of neighbors. Okay? Yes? No, p is of order 1. I'm going to speak about this. So the question was, if p is smaller than 1? So here p is of order 1. It's an order 1 number, but as we're going to see, it can be either smaller or larger than 1. And as you've anticipated, it's going to be important. So in the rest of these lectures, I'm going to call k the degree of a node, okay, which is the number of neighbors. And so what I just shown is that the average value of k is equal to p. But you can be a little more greedy and ask, what is the full distribution of k, which I'm going to call p of k. This is the distribution, degree distribution. So how would you do this? Well, if you want to know how many neighbors a certain node has, it's going to be the number of ways to choose k among n minus 1 times p divided by n to the k, 1 minus p divided by n to the n minus 1 minus k. So it's a binomial distribution. But I'm not redoing the calculation. It's always the same calculation. In the limit when n goes to infinity, this binomial distribution becomes a Poisson distribution. And so what I get is that in this case, in the Adarsh-Renyi case, this is the Poisson distribution that we've seen already today, which is p to the k exponential of minus p divided by factorial k. Okay? So this is a very simple graph, and it has a very simple distribution, which is the Poisson distribution. And note that this distribution decays extremely quickly when k increases. So, if you want a numerical example, if I take p equal 1, so the average degree is 1, then the probability to find a node with 10 neighbors, which is not that big, it's just 10 times the average, this is already like 10 to the minus 7. So the Poisson distribution is a little bit like the Gaussian distribution that I've talked about. It's an extremely thin distribution, thin tail distribution that decays incredibly quickly as k increases. And therefore, it's a graph where there's no hub. There's no site that has a very large degree, that has a very large number of neighbors or of friends, if you think about a social network. And we know from empirical data that many graphs are actually scale-free in the sense that they have a power law distribution of degrees. Some nodes have an incredibly large number of neighbors, while others have a small number of neighbors. So I'll go back to that in the next paragraph on scale-free networks, but let me tell you a little more about what happens in the Adarsh-Renyi network. Well, although everything looks simple, there's still something non-trivial that happens in the regime where P is over the 1. And what happens is related to the question that someone asked in the room. We have 2 students today in the room. And please, if some of you want to come, we can organize that others take their turn. So what happens is that there's a phase transition in Adarsh-Renyi networks, which is that when P is less than 1, there are only finite size clusters. So all this is, of course, in the limit where n goes to infinity. So when P is less than 1, I only have, things like this, isolated nodes or nodes that are connected to only a few other nodes in the same cluster. But if P is greater than 1, there exists a giant component. So GC is going to be giant component, which means that if I pick a node at random, there is a probability P infinity, which is greater than 0, that this node belongs to an infinite cluster, okay? So it doesn't mean that this probability is equal to 1. I may still find nodes that are in isolated clusters, in finite size clusters, even nodes that are completely alone, okay? By the way, the probability for k to be 0 is always non-zero. It's exponential of minus p. So there are always isolated nodes. P of 0 is exponential of minus p. So clearly, even when p is greater than 1, there are isolated nodes. But there is also an infinite size cluster, which is called a giant component, or it's also called in physics a percolation cluster. So you'll see these 2 names depending on the literature, giant component or percolation cluster, but it means the same. And in my egg white analogy, it's when P is greater than 1, then when you pull on a node, imagine that you're actually taking an optical tweezer and grabbing a polymer and try to pull on it. Well, if you're in the P less than 1 phase, you're going to only pull finite clusters. So it's going to be easy, and the thing is a liquid, so it's the reason why it's easy. But if you're in the percolating phase, then by taking a node at random, you might have to pull the entire system, which means that it's a solid. Okay, so this is not a trivial effect that happens in these Adarsh-Renyi networks. And I'm going to speak more about the existence of giant components. So why is it P equal 1 that makes the difference here? And the stability of these giant components a little later. So this was my first construction of a random network, the Adarsh-Renyi, which is simple enough. But as I said, it's disappointing, quote unquote, because there are a lot of networks for which this Poisson distribution of degree falls short of explaining what's going on. I mean, as I said, the probability of having a node that's highly connected is so small that you're never going to be able to describe social networks, for example. So let's look at another construction. Scale-free networks. So these constructions are meant to generate much broader distribution of degrees, and the most famous of them is due to two physicists, Barbasi and Albert, and that's a model from 2000. And it's an incredibly popular model. With this paper of Barbasi Albert has an amazing number of citations. I don't know, it already has like several tens of thousands citations. It's cited in physics, in computer science, in biology, and in many different fields. By the way, I told you at the beginning of these lectures that if you look at the distribution of the citations a paper has, it's a very broad parallel distribution, and this clearly is one of the paper contributing to the tail of the distribution of citations. And by the way, citations can be thought of as a network. You know, if you put a link between a paper and another paper when the second paper is citing the first, then you construct a network. And that's a little bit the type of models that we're going to construct here. So what I'm going to tell you about is a model that is grown dynamically. So there's some kind of dynamics. It's a dynamical model. And it works as follows. So I'm going to start at t equals 0 with a single node. Then at t equals 1, I'm adding a node. And with this node, I'm adding a link. So each new node adds one link in the system. And of course, at this stage, there's no choice. The link has to go to the previously present node. Then at t equals 2, I already have these two guys. And I'm adding one more node, and this node has to connect to one of them. And in this case, they have the same degree. Each node, already present node, has degree 1. And so in this case, it's going to be with probability 1/2, 1/2, I'm connecting to one of these two nodes. So at this level, nothing much happens. But then at t equals 3, when I'm adding a fourth node, then the rule will be that I'm attaching the new edge preferentially to nodes with high degrees. And the rule will be that I'm attaching with a probability that's proportional to the already existing number of neighbors, so to the already existing degree. So here you see that I have 3 choices, but the probability to connect to this thing will be twice the probability to connect to these other two guys. So I have a probability 2/3 to be connected to this one, and 1/3 to be connected to one of these two. And so you see what's going to happen. So sometimes I'm going to connect to this one, but sometimes I'm going to connect to that one. And because I'm connecting to that one with higher probability, it's again going to increase its degree. And the next time step is going to attract even more links. So it's a kind of rich get richer effect. And if you are following these lectures since the beginning, you have already recognized proportional growth models, because in a sense, the more you have grown, the more likely it is going to be that you grow again. And we know already that these types of models tend to generate power laws. Okay, so at time t, I have a bunch of nodes, and the first node has K1 neighbors, the second node is K2 neighbors, and so on. So I have these degrees, and what I know is that each time I add a node, I also add a link, and this link connects to two nodes. And therefore, the total degree of the network is twice the number of links I've added. You see here, for example, I have K1 equal 1, K2 equal 1. So the sum over I of Ki is equal in general to 2 times T. It's equal to 2 here, it's 4 here, and so on. Okay? And the rule of the game will be that I attach to the I site probability to attach to I is equal to Ki divided by the sum of the Ki's, which is 2T. And so this is what's called preferential attachment. And precisely, it's preferential in a linear way. The more degree you have, the more likely it is to become the target of the new incoming node. So you can ask, why do I choose a strict linear relation here? Well, I'm going to give you generalizations of this result later on, at least discuss them quickly. But it seems reasonable that in many cases, your popularity is going to be linear. For example, if you think about papers, the more a paper is cited, the more likely it is that you're going to see it cited in a paper you read, and the more likely it is that you're actually going to cite your paper, the same paper as well in your own paper. So of course, this has to be decided on an empirical basis, but it turns out that in many cases, this is not a bad approximation. Okay, so now how does it work? So the first thing I want to emphasize is that this dynamical process is stochastic. It's not a deterministic process. You see, each time step, there's a choice. I said here, I've chosen to connect to the most likely site, 2/3, but of course with probability, I'm sorry, I've said something wrong here. You should have stopped me. This doesn't sum to 1. That's the problem when, so this is 1/2, 1/4, 1/4. I'm surprised nobody shouted, but anyway. So what I'm saying is that there's a higher probability to connect to that one, but it could have been that in another history, in another world, I would have connected to this one. Okay, and then this one and this one would have had the same degree at the next time step. So I'm generating an ensemble of graphs that are not all the same. And so I can speak about averaging over histories in this model, okay? And that's what I'm going to introduce now. I'm going to call n of k and t. This is the average number of sites, of nodes, with degree k at time t. And it's the average over what? It's the average over all possible histories of the construction, okay? And so having understood that it's an average over constructions, it's very easy to come up with a recursion relation for n of k and t. So let me write it, and then I will comment and justify. So what I'm claiming is that n of k and t plus 1 is n of k and t plus k minus 1 divided by 2t n of k minus 1 and t minus k over 2t n of k and t plus delta of k and 1. So this is the fundamental equation, the master equation, if you want, that I want you to understand. So what does it mean? It means that in order to have k, degree k at time t plus 1, then either you had the number of sites is at time t is n of k and t, but you can add to this number of sites that have degree k by connecting the new incoming node to a site that had degree k minus 1. And this happens with probability k minus 1 divided by 2t. Remember, this is this. So on average, it's going to be the probability to connect to a site, to a node of degree k minus 1 times the average number of such sites. But if you connect to a site, to a node with degree k, then you're taking away some of these nodes from the count. So there are less, at time t plus 1, there are less nodes with degree k, and this occurs with probability k over 2t. So there's a minus sign here. And then every time you add a node, you add a degree which is equal to 1, because the incoming node always has a degree equal to 1. See this guy here, it has only one edge going out, and so this explains the delta of k and 1 here. So what can we say about this equation? Well, it's very natural to think that the number of nodes of degree k at large times, well, first let me write it this way. It's natural to write it like that. T times P of k and t, where because the total number of sites is sorry, I'm using sites and nodes to mean the same thing. So the number of nodes is t plus 1. So maybe I should write t plus 1 here. And doing this, I'm defining not the number, but the probability. This thing is the probability that a node has degree k. So that's a definition if you want. But then my assumption will be that when t goes to infinity, assumption, which is very natural in a way, is that when t goes to infinity, p of k and t converges to a stationary distribution, which I'm calling p star of k. Okay, I'm repeating this process over and over again. So the number of sites, the number of nodes is increasing. So I take care of that by introducing this factor t or t plus 1 here. And then at very long times, I'm expecting this distribution to reach a stationary state. So with these two items, this one and this assumption, I can plug into the master equation above and find an equation for the stationary state itself. And so what you find, again, I'm not detailing the calculations, but it's really easy to do that. Just take this, plug it in here, and then assume this to be true. And then what you find is that P star of K obeys the following discrete equation: 1/2 of K minus 1 P star of K minus 1 minus K P star of K plus delta of K1. So the 1/2 here comes from the 1/2 that's here. K minus 1 P star of K minus 1, this is this guy. K P star of K, this is this guy, and delta of K1 remains unchanged. Okay. So this is the equation you should solve to get the stationary state of this Albert-Barabasi model. And it's fortunate, but it happens that this equation can be exactly solved. And what you find and again, this is a little exercise if you want to check it yourself. But what you find is that P star of K equals K4 over K plus 1, K plus 2 is an exact solution. Okay, so just have to put it in there and check that it works. And this thing happens to be normalized to 1, so it's a correct probability distribution. And what you can notice is that when K becomes large, this decays as 4 over K to the 1 plus mu, with mu equal to. So this mechanism, this rich get richer mechanism, this proportional growth model, leads to an exponent, which a power law tail with an exponent which is 2. So the average degree exists, but the variance of the degree distribution is infinite. Okay. So that's one possible model. There are many variations around this model that you can consider. For example, you could consider an attachment rule, so some variations. So you could have an attachment rule that's proportional to K, which becomes proportional to K plus some intercept. Okay. This is proportional. So it's still linear at large K, but there's an intercept M. And in this case, you can also show that the solution is a power law with an exponent mu that depends on M. Okay, so that's a natural change. But maybe you want to make a more drastic change. What happens if your attachment rule is proportional to K to the beta? So beta equal 1, this is linear attachment, which leads to power laws. When beta is less than 1, but greater than 0, then I'm not doing the calculation, but what you get is that P of k is not a power law anymore, but it decays as exponential of minus k to the 1 minus beta. So this is called the stretch exponential. You see, it's when beta is positive, it's slower than any exponential, but it's faster than any power law. So it's an intermediate regime. And what happens if beta is greater than 1? Well, when beta is greater than 1, you're in a situation that, in a sense, is similar to the situation of the Hawkes processes when R0 is greater than 1, in the sense that this assumption here is no longer true. There's no stationary state, because you see that the attachment rule grows so quickly with k that there's condensation. In the sense that a finite number of nodes attract everything and have a degree that grows with t in an unbounded fashion. Okay, so here you have a completely different regime where there's no proper stationary distribution for P of k. So in a sense, if you want to have power laws, this is the only case which naturally gives rise to power laws. So if you have a power law degree distribution in your empirical network, then presumably this is because there is a process behind it, which is a linear preferential attachment process. Okay. So this is what I wanted to tell you about networks. I mean, about the construction of networks. So two very different constructions. Of course, I'm not exhausting all the possible ways to build networks. I'm only giving you two extreme cases. Erdős-Renyi, which leads to Poisson distribution of degrees and is the classical network model, and the Barabasi-Albert model, which leads to a power law distribution of degrees. But you can invent many other ways to build networks, and they have to be analyzed on a case-by-case basis. But what is important from a technical point of view is, and I encourage you to think about this more if you haven't followed all the steps, but behind all these models, there is often a master equation, an evolution equation like this. And so this is really, from a technical point of view, the main message of these lectures. Okay. So let me now talk about the giant component. The existence of a giant component. So I've already insisted on why it's important to know whether in your network there is a giant component or not. So what tools do we have to answer that question? I have a given network. How can I know analytically, from a theoretical point of view, whether or not I have a giant component? That is, whether or not my white will be solid or liquid, or whether or not my epidemic will propagate among a social network, and so on, or whether a crisis will propagate across a firm network and invade the whole economy or be localized in some subparts of the economy. Okay, so this is a very important question indeed. So what I'm going to give you as a tool to answer that question is a little bit of a hand-waving argument, which relies on everything we've understood about branching processes. It's going to be actually restricted to some types of graphs, which are what one calls tree-like graphs. So I'm going to explain in a minute what's a tree-like graph, but you can think of it as an approximation for graphs, for arbitrary graphs, to treat these graphs as if they were trees. But some graphs are really very close to being trees, and for which the approximation I'm going to talk about actually is exact. And what I'm going to derive for you is the so-called Molloy-Reed criterion. So this is going to be called the Molloy-Reed criterion for the existence of a giant component. But the way I'm going to present this Molloy-Reed criterion is a little bit hand-waving. If you want to have a more mathematical proof of the Molloy-Reed criterion, I'm going to, if I have time, give you a hint of that later on. Otherwise, you will find it in the notes that I'm currently writing, or actually in the Ecole Polytechnique lecture notes. But the way I'm going to present it, I think is nice because it emphasizes the relation with what we've seen already, branching processes, and I think it's a very nice way to see things. Okay, so what's a tree? So a tree is a graph with no loops. So for example, this is a regular tree, and you see I can continue that to infinity. It has no loops. Sometimes I have loops in my graph, but the loops are not small loops. They are long loops. So maybe, for example, I continue the construction here, and at this point, these 2 points merge together. So there's a loop in my graph. But the loop here, it's not that big, but you can imagine that if these loops are big enough, so it means that in a sense they're rare enough, I can view locally the graph as a tree. And so if you look at, for example, the Erdős-Renyi graph, well, in the limit where close to the appearance of the giant component, the very large clusters in an Erdős-Renyi graph, they're in a proper mathematical sense tree-like. There are some loops, but they're somehow very large compared to one. The size of the loop is much larger than one. So, for example, it grows like the log of the number of sites. So in some cases, you can really justify the approximation that I'm going to present to you. In other cases, the graph is really a tree, so it's exact. And in still other cases, it's just an approximation. So for example, let me give you a graph that's not a tree. So if you take a Euclidean lattice like this, then you see that there's no real meaning in saying that it's a tree, because even at the shortest length scale, there are loops. Okay, so this is not a tree. But even if it's not a tree, you can deem it as a tree, treat it as a tree, and what I'm going to tell you about is just an approximation, which has no reason to be good, but you can try it. And in some cases, it's a very good approximation. In other cases, it's actually an exact treatment, an exact argument. Okay? So my argument is about tree-like graphs. So if I have a cluster that's a tree, or a tree-like object, I can always think of this tree as a genealogical tree. Okay? Of course, it has nothing to do with population growth, but I can think of the tree as something that has some temporal structure where I choose a node arbitrarily. This is the ancestor. And then these guys are the children of the first ancestor, and these guys are the children of the children, and so on. Okay? So I'm just thinking of a tree like a genealogical tree. So you see that if I have loops, it doesn't mean anything, because if I have loops, it means that I can be the child of my children. But if these loops are rare enough, I can forget these anomalies and think of that as a genealogical tree. And so what I know is that my genealogical tree is growing. So this tree is of finite size so the family that has this guy as an ancestor has a finite size if the reproduction rate R0 is less than 1, and it can be of infinite size if R0 is greater than 1. Okay? And R0 equal 1 is this strange critical thing that is in between. So if I want to know whether there's a giant component, I want to know whether there can be infinite size clusters in my graph, right? That's the same question. So I have to answer the question in terms of population growth, is whether the reproduction rate in this fictitious tree, in this fictitious genealogical tree, is this reproduction rate greater than 1 or less than 1? Okay, so this is the question that I'm going to try to address, and it's going to lead to the Molloy-Reed criterion. So what I'm going to need is to describe my tree in terms of the probability of the degree distribution. So the only ingredient I'm going to need is this object P of K. This is the unconditional degree distribution. And I'm insisting on unconditional here, which means that I have my graph, my network. So maybe it looks like this, okay? And what unconditional means is that, I'm picking at random this node and asking what is the probability that this node has degree K. This is P of K. And you'll see in a second another degree distribution which is going to be conditioned and which is not going to be the same as P of K and which is going to play a crucial role. So I'm assuming that each node has an independent degree, and each of these degrees is drawn according to P of k. Okay. Nodes have independent so ID if you want across nodes. So there are no correlations between the degrees. It's not because this one has a high degree that its neighbor will have a high degree. Okay, so this is P of k. Now, you should pay attention because I'm going to introduce, and unfortunately, of course, as usual, I won't have time to finish today. That's too bad. But let me at least go until the Molloy-Reed criterion. So what I'm claiming is now that I'm going to do another construction to introduce another degree distribution, which is the following. I'm going to take a node at random, like before, this one, and then take an edge out, which is outgoing from that node, and target another node. Okay, so I've taken this node at random. I've chosen this particular edge, and I'm landing on the second node. So this, if you want, is I0, which is the node I chose at random. The degree of that node is distributed according to P of k. And now I'm looking at another node, which is a neighbor of mine, and I'm asking what's the distribution, the degree distribution of this guy, J. Okay. So think of it in terms of your friends in a social network. I'm taking one guy at random on a social network, and I'm counting the number of friends. This is distributed according to P of k. Now I'm taking one friend of this guy, and I'm asking, what is the degree distribution of that guy? Okay. And what I'm going to say is that this degree distribution is what I'm going to call Q of k. So it's the degree distribution of a neighbor, of a friend. And what I'm claiming is that Q of k is not equal to P of k. And there's a clear reason already for that to be the case, which is that you see that this node here has 0 neighbors. So if I choose at random a site in my network, I have a certain probability to find that P of k equals 0 is non-zero. I mean, I have a probability to find a node without any neighbors. So because P of k equals 0 is non-zero, these are the guys that I'm going to choose. But this guy has absolutely no chance of being chosen as a friend because he has no friends. And if you think about this process of choosing a friend is going to select preferentially friends who have a large number of friends. Because the more friends they have, the more likely it is that you are one of his friends. And the more likely it is that you're going to choose him in your selection process. So you can make this argument precise by using Bayes' theorem, for example. And what you find is that Q of k is k times larger than P of k because of this amplification effect. Because there are k ways of choosing a neighbor with a large degree, it's going to be chosen more often through this process. Okay. So if you want to have a normalized distribution, I should divide k P of k by the expectation, the average value of k in P. So I've defined EP of k as the sum from k equals 0 to infinity of k times P of k, such that the sum over all k of q of k is equal to 1. Okay. And now something strange happens, which in a sense is contained in my argument, is that if I compute the average value of the number of friends of my friends, which is EQ of k, this is equal to sum over k of k squared p of k over e p of k, which is e p of k squared divided by ep of k. And I guess that I shouldn't go further than that. And this is larger or equal than ep of k. So the average number of your friends is larger than your average number of friends. So this is called the friendship paradox in networks, which means it's very frustrating, but it means that that's this selection bias, the fact that your friends are, by mechanistical way, more have more friends than you on average, means that they're more popular. Okay, so this is going to have a very important consequence for vaccination campaigns, but let me come back to what I was interested in, which is the existence of a giant component. So what I'm claiming here, and I'll be done in 5 minutes, and then unfortunately then next week is vacation, so there will be a 2-week gap for me to come back on the last little thing that I wanted to talk about, but it's I don't think I should do that today. It's going to be too long. So what I'm saying is that, these children, by construction, they are children of an ancestor. And so they are, in my analogy, they are friends of a guy. And so if I want to know the distribution of degrees of these children, I have to use Q of k and not P of k. And so what happens is that R0 is equal to the average number of children, which is the expectation of k, the average degree under Q, because again, these are not random people, they are people selected as being the child of someone or the friend of someone, minus 1, because one of the links is the one that defines their ancestry. Okay. And so the Molloy-Reed criterion is that R0 should be greater than 1, which translates into EP of k squared. So EQ of k, I said it's EP of k squared divided by EP of k. So here I have EQ of k must be greater than 2. So EP of k squared must be greater than 2 times EP of k. So there exists a giant component if and only if this criterion holds. Okay. So that's what I wanted to arrive at. So you see that I've been very hand waving here. I've used this genealogical tree analogy, and I've relied on the branching process, on what we saw last week about the Galton-Watson model. But I assure you that there's a better way to do all this, which involves more mathematics. And so I didn't want to go into the mathematics, but you can certainly have a go in the lecture notes to see how you do this a little better. Anyway, let's do the Erdős-Renyi case. ER is Erdős-Renyi. Erdős-Renyi means that P is a Poisson distribution. So the Poisson distribution is such that EP of K squared is equal to P squared plus P. Why? Because the variance of K is P. So the variance is the average of K squared minus the average of K, the whole thing squared. So that's what I get, T squared plus P. And the average of K is P. So I have that this must be larger than twice than 2P, which means that P must be greater than 1. And so we recover what was anticipated by some in the room, that if P is greater than 1, in the Erdős-Renyi graph, you have a giant component. Let's see what happens in the Barabasi-Albert model. You remember Barabasi-Albert? We had that P of K was decaying as 1 over K cube, which means formally that the average value of K squared is infinite. So for Barabasi-Albert, there exists a giant component. And the reason is that, because of these hubs, because there are nodes that are so connected to many others, then different parts of the subgraph will likely be connected together through these highly connected nodes. Okay. So again, in the epidemic analogy, these are super spreaders, and because of their existence, the disease is going to spread very quickly in the population. But at a formal level, we see that the Molloy-Reed criterion tells you immediately that Barabasi-Albert graphs have a giant component. Okay, so what I wanted to tell you about is, okay, there is a giant component, catastrophe, the epidemic is propagating. What can I do to prevent it, to cut the spread of the disease? And this translates into how robust is this giant component if I start removing some links. So imagine that through vaccination, I'm removing some of the links of that network. How many links should I remove to kill the giant component, to make such that the giant component disintegrates and there are only finite clusters? So this is a question that we can very easily answer with the formalism I've given you up to now, but I think I have to stop at this point, unfortunately. So that's me for today. I don't know if there are questions.
I have a question.
Yes.
Can you explain again the expression of Q of K on the upper board? Why I don't really understand why it's equal to K of K over the expectation.
Okay, so the proper way is to use the base argument, but intuitively it means that, as I said, if J has a large number of neighbors, okay, it's highly probable that U will be one of them. So okay, the more J has neighbors, the more probable it is that it's going to be selected through this mean that I explained. That is, I first choose I0 at random, and then I choose J as a friend of I0. But if J is a friend of I0, it means that I0 is a friend of J. And because J has many friends, it's going to be much more likely to choose J if J has many friends than if J has a few friends. And in the extreme, you see that if J has no friend, there's no way to select J using this procedure. And that's exactly what you find here. When K is 0, Q of 0 is 0. There's no way to choose a neighbor with 0 neighbor yeah. It's impossible to choose J if J has no friends. So this is an extreme case, but you can intuitively understand that the more K, the larger K, the more probable it is to choose a certain J. And as I said, I didn't do the argument in a rigorous way, but if you want to do it in a rigorous way, you can think of it in a biased fashion.
Okay. Okay, thanks. Nice theorem. So what is the probability that I'm chosen knowing that I have k neighbors? And it's the probability that I have k neighbors times the probability that I'm chosen, but the probability that I'm chosen is proportional to k. Okay? Okay.
Other questions?
Can you explain again how you obtained the criterion?
So what I'm saying is that these guys, they're Freds. They are selected as I've explained here. So the degree distribution of these people is Q of k. And because the degree distribution of Q is Q of k, the average number of children is the average degree minus 1, because there was one link that comes from the ancestor, from the parent. So the number of outgoing links here minus the one that makes him or her a child is the expected value of k in Q, because I have to use Q and not P, minus 1. And the minus 1 here counts away the ancestor. It's the new links coming out of the selected child. But you know, make no mistake. I know that this is a rough argument. This is a kind of hand-waving argument. But I thought that it was maybe more interesting to present this in this way for you to understand the deep analogy between the existence of a giant component and the criticality of branching processes, which we've seen last time, rather than to give you a more formal way to think about this problem. As I said, there's a way, and you'll see them these calculations in the notes. There's a way to be much more precise in this, and in particular to compute the probability for a node to belong to the infinite cluster. So what I call P infinity. You see here, I have no way of computing P infinity. It's just an existence criterion, but it doesn't tell me what the probability to belong to the giant cluster is. Whereas the more technical approach to this problem gives you an answer for P infinity. And of course, it gives you that P infinity is non-zero when E of Q is greater than 2.
Thank you.
Okay. Well, have a good vacation week, and we'll see each other, quote unquote, first week of March.
Thank you. Bye.
Thank you.
Thanks. Bye.
This conference will now be recorded.
Okay, great. So let's start with this last day before the holidays. So as you see, we kind of catched up with the lecture because this today is about Hawkes processes that have been discussed during the lecture today. But it is a little bit long, so what we're going to do is to split it into two. So today we will do only the first part, which is a little bit connected to what was discussed in the lecture. So in particular, it focuses on linear Hawkes processes. And then the second part, which is about nonlinear Hawkes processes and metastability, this will be postponed to the 10th of March at this point. And instead, what we can do in the remaining time today for those who are interested is to go back to what we left behind from TD3, which was the derivation of Fokker-Planck for multiplicative noise. And I just want to sketch how you derive it, both in the Ito and in the Stratonovich prescription, and just to tell you how to compute stationary states, which is pretty easy. Okay, a comment. So unfortunately, I realized that the notation of the TD and one of the lectures are totally messed up. So what I will do is this afternoon to somehow modify the TD in such a way that we stick to the notation of the lectures. So I will upload a version with the solutions which is compatible with the lecture. But in here, since I gave you the text already, I think it's better to stick to the notation that we have in the text. So one has to be a little bit elastic. So what I did is to call the kernel that in the lecture was K. Now I call it phi. Then what was called rho 0, as you will see, becomes alpha in here. The average, let's say, rate that was lambda bar, I will call it G infinity, because of this ergodicity, you can also relate it to somehow the stationary value of lambda. And then we will be working today with exponential kernels. So in the lecture, the let's say decay time was 1 over alpha. Here, since we use alpha instead of R0, I will introduce beta. So forgive me for this notational issue, but keep in mind that somehow we are talking about the same things. Okay, so let's go to then exercise 1. So let me recall the expression for this conditional intensity of the Oakes process that I call lambda t. So this is given by some background intensity, lambda 0, which was mu in the lecture. And then you have the term with a kernel that, as I say, I write it as alpha, sum over all the events that happened before the particular time t that we are looking at, of some kernel at t minus ti. And as it was said in the lecture already, we can rewrite this discrete sum in the following form. So as an integral from time, let me say 0 to time t, 0 or minus infinity, it doesn't change much, of the kernel, so f of t minus tau, and then you have the differential of your stochastic process that counts how many events you have at time tau, tau plus d tau, that I denote in this way here. And let me stress that this is a conditional intensity because it is conditioned to the history of the process. So you assume that you know what is the history up to time t, so which events occurred and at which times. And then once you know this, you can write down what is, if you want, the probability to have an event at a later time t plus dt that is controlled by this lambda t. Okay, then there were several things that were already introduced. So in particular, what we are going to look at in here is the clustering ratio. So in the lecture, it was discussed the value of the clustering ratio somehow at infinite time, so the stationary value. But here, let me introduce some more general time-dependent rho of t that we are going to compute. And let me define this similarly to the lecture as the variance, by this v I mean the variance, of the number of events at times t plus tau minus the number of events at time t. Yes? There was a question? Oh, okay. Divided by the average of this difference. And you see that what I have on the right-hand side is something which in principle depends on t, but I'm assuming that this, let's say, clustering ratio only depends on the time difference, and this is some assumption of stationarity that holds in the phase we will see whenever alpha is smaller than 1, so whenever you have the process is eventually ergodic. So this is the clustering ratio. And what we're going to do in here is to compute this clustering ratio for any value of time, tau, for one specific kernel that was already introduced in the lecture, which is the exponential kernel. So in here, we are going to focus on a kernel that is of the form beta e to the minus beta tau. And we are going to compute this through an equation which relates the clustering ratio to correlation functions. So that gives you the correlation between the number of events at different times. And this is something that is defined in the TD in equation 4, I think. So let me not rewrite equation 4 and equation 5, but this is what we are going to use to compute this object in here. And so just as a comment, actually, let me introduce another quantity first. So we are going to first of all compute what I call in the TD g of t. And g of t is defined, so as it was stressed already in the lecture, this quantity, this conditional rate, is a random variable itself. And it is a random variable because it depends on the history of the process. So once you know the history, you know what is lambda of t, but in principle, the history is a stochastic process. So you have fluctuations depending on the different realizations. And what we're going to introduce is the average of this quantity with respect to this history, or if you want, the ensemble average E of this conditional rate, lambda t. And we're going to solve the equation for this g of t. And what was discussed in the lecture was essentially the solution of this equation in the long time limit. So the quantity lambda bar was what I call g infinity. So it's the limit t going to infinity of this g of t. And it was given a self-consistent equation for this lambda bar or g infinity, and we will recover in here the results for this, which is of the form. So if you remember, g infinity will be equal to, in this notation, lambda 0 over 1 over alpha. Or in the notation of the lecture, it was mu divided by 1 minus R0. Yes? No. Okay. Good. And the other quantity that was given in the lecture was the infinite time limit of this clustering ratio that was, in our notation, 1 over 1 minus alpha to the power 2. And this is something that we will derive right now for the exponential curve. Okay, so let's do it. So the first point, do you see this? Yes. The first point is to use, so this is going to be an exercise on Laplace transforms, basically. And what we have to do is to solve the equation for this g of t. And the equation reads as follows. So I can directly derive it from up there. Hopefully, yeah. So if you see, I have the equation for lambda t up there. And what I can do is to take the expectation value on the left-hand side. And then I take the expectation value on the right-hand side. And this, I bring the expectation inside the integral there. And I will have the expectation value of the differential of my stochastic process. And then I remember that lambda of t was defined so that if you want the proper definition of lambda t is of a conditional expectation value of having events in a small interval t plus dt conditioned to the history of the process up to time t that I will denote as h of t. Okay, so if I have this lambda t and then I take also the expectation with respect to the history, what I get out is simply the ensemble average, now averaging over all times of my ds. That is what will appear in the right-hand side if I take the expectation of this equation. So these were many words, but somehow you can easily realize that the equation for this g of t is nothing but lambda 0 plus integral, there was an alpha in front, integral from 0 to t in d tau of phi of t minus tau times the very same function g of tau. So this is a self-consistent equation, an integral equation for g that we want to solve. And as you see in this equation, what you have on the right-hand side is a convolution. This is some sort of convolution. So there is a theta of, so you're asking here that tau is smaller than t, so there is a theta of t minus tau. So I can rewrite this, if you prefer, in this way. And then you recognize that we have a convolution. And we know what we have to do when we have convolutions. So there is a very useful instrument or trick that we can use to solve this type of equation. And this is either Fourier or Laplace transforms. So in here, I will use Laplace transforms, and I will integrate only over positive times. And Laplace transforms are useful because anytime you have a convolution, they allow you to somehow rewrite in terms of Laplace transform the equation in terms of a product. So let me introduce the notation first. So the Laplace transform of a function g, that will be a function of s now, is simply the integral from 0 to infinity in dt e to the minus st times my function g of t. And so if I take the Laplace transform of this equation here, so now we will call this g hat of s. This is a function of s. Let me apply such a transform to this equation. And if you do this, you will realize that this gives you g hat of s equal to the Laplace transform of a constant that I will compute in a minute. That's very simple. Plus, as I said, so this is an exercise that if you want, we can do at the end if you have questions, but it's very easy to see that here you will end up with a product of the Laplace transforms of these two quantities in here. So I will simply have the Laplace transform of my kernel evaluated at s times my function transformed evaluated at s. Okay. And this is nice because now this is just an algebraic equation for my function in Laplace space. So what I have to do is to compute these two terms that I have in here. So the first one is the Laplace transform of a constant, but this is very easy. So if you just put a constant in here and you integrate the exponential, you just get a factor of 1 over s times the constant. So this means that this is lambda 0 over s plus alpha g hat of s. And then we plug our assumption that the kernel is exponential. So let me compute this phi bar of s, assuming that phi has the form up there. So this is again just an exponential integral. So this will be the integral from 0 to infinity in dt of e to the minus st times my function phi, which is e to the minus beta t. Okay. And so you see that, again, doing the same exponential integral, you have b divided this time by a factor b plus s. So I plug it in here. So I have beta, sorry, not b, but beta divided by beta plus s. Okay. And now let me solve for g of s. So I hope that you see. Yes. So then I have that g of s. I collect all of the terms. So I will have 1 minus alpha beta over beta plus s. This is equal to lambda 0 over s. And therefore, g hat of s is now very simple, is lambda 0 times beta plus s divided by s times beta. I have beta minus alpha beta plus s, so I can write this as beta 1 minus alpha plus s. Okay, so this is the solution in terms of Laplace transforms. And now, of course, once we have this, what we have to do is to do the inverse Laplace transform to get the solution as a function of time. So let me briefly recall how you do or how you define the inverse transform and what is the usual trick to compute it, which is the residue theorem. So first of all, what is the definition of the inverse applied to my function g hat of my Laplace transform? So this will be a function of t again. And this is defined as you have a factor of 1 over 2 pi I. And then you have to perform an integral in general in the complex plane along a contour which is usually called the Bromwich contour that I will just write and then I will comment. So it's an integral along a vertical axis in my complex plane where the real part is equal to some constant gamma, and then I integrate over all the axis. So from gamma minus I infinity to gamma plus I infinity. Of what? Well, the integral is in ds. Now s is a complex variable in general, and then I have e to the st, so the reciprocal of the factor that I had in the direct transform times g hat of s. Now, how do you choose gamma? Well, you can choose it more or less arbitrarily, but with a constraint that if you are doing the inverse transform of a function which has some singularities on the complex plane, you have to choose gamma in such a way that you are always at the right of the singularity. So let me give an example. So now this is my complex plane for the variable s, real and imaginary part. And let me assume that we want to do the inverse transform of some function which has some poles or singularities on the complex plane. So for instance, let's go back to the function that we have. As you see, you have two simple poles of this function, one at s equal to 0, so you will have one pole here, and another one at s equal to minus beta times 1 minus alpha that we assume, well, you can take arbitrary sign, but in the drawing, let me assume that 1 minus alpha is positive, so that the pole is negative. So you have two singularities, and you have to choose gamma to the right of this singularity. So whatever vertical line that is to the right of 0 in this example would be a good contour for me to perform this integral. And since the function is analytic, I can move it back and forth, provided that I do not hit any singularity. And then once I have this contour, the usual trick to perform this integration is to close the contour, or one way, if you want, to perform the integration is to close the contour at infinity. And this is good because it allows me to use the so-called residue theorem, which tells me how to compute integrals over closed contours on the complex plane by summing the residues of the function at the singularities which are inside the contour. So first, let me comment why it's not dangerous to close the contour at infinity. Well, this is so whenever you have a function which decays sufficiently fast at infinity. So in this case, you have a decay that is 1 over s squared. So you know that the contribution along this big circle will go to infinity if I send, will go to 0, sorry, if I send the radius of the contour to infinity. So these pieces of the contour will not eventually contribute, but they allow me to close my contour of integration. And then I can use this residue formula that I'm sure you know. So suppose that I want to compute an integral over a closed contour that I call now capital gamma of a function f of z dz. So this residue theorem tells me that what I have to do is to sum over all the singularities that I have inside the contour, the residues of the function at those singularities. So I will get, there is a factor of 2 pi I, which I'm happy about because it will cancel this one. And then I have a sum over all the singularity that I call Zi. So for instance, Zi are eventually the poles of my function f of z, of the residue of the function f at the points zi. And if I have simple poles, so if you have never seen this before, just let me know, but otherwise, let me just remind you. So if you have simple poles like in here, computing the residues is very, very simple. So what you have to do is essentially so if you see in here, I have a pole at s equal to 0. So the residue of this function will be given by, you multiply the function by s minus the value at the pole. So in this case, it would be just s. And then you compute what remains exactly at the pole. So, okay, let me write a formula just to be concrete. Here. So if you have a simple pole, this means that your function will be of the form, let me say, g of z divided by z minus zi, which is the pole. So this is my f of z. And then the residue of f at zi is, space, the limit z going to zi of z minus zi times f of z. So it is just essentially the value of what I call g in here, computed at zi. Okay, so let's use this then to compute the inverse Laplace transform of my function g hat. Do you see this? Yeah. Yes. Okay, so what will be g of t? So I will have a factor of 1 over 2 pi I, which I cancel with the 2 pi I coming from the residue theorem. And then I have the sum over my two singularities, Si. So Si is either 0 or minus beta times 1 minus alpha of the residue. Now, what is the function of which I have to compute the residue? So if you see from up there, I have g hat times the exponential factor, which I don't have to forget. So it's g hat of s e to the st at the points si. Okay, so for our example up there, so as I say, the first pole is at s equal to 0. So if I compute the residue there, I just get lambda 0 times beta from the numerator. The exponential computed at s equal to 0 gives me 1. And then below, I have beta times 1 minus alpha, because s is equal to 0, plus the contribution of the second pole. So the second pole is at minus beta 1 minus alpha. So I will have at the denominator just beta times 1 minus alpha, which comes from the factor 1 over s. And then I have up here lambda 0. Then I have beta plus s computed at the pole. So this gives me beta minus beta. So this is just alpha, I think. And then the exponential, which this time is non-zero, is e to the minus beta 1 minus alpha times t. Okay. So beta here simplifies. So let me write it as lambda 0, 1 minus alpha. And then I have 1 minus alpha times this exponential factor. Okay. And this gives me, for any time, the average value of the conditional intensity. So from here, you can now connect with what was said already in the lecture. So the first thing that you can see is that for this simple case of the exponential kernel, you have, so let's assume now that 1 minus alpha is positive. So alpha is smaller than 1. And remember that alpha was rho 0, I think, in the lecture. So in this case, the process is stationary and it will be ergodic. This factor in the long time limit will decay to 0. And you will find that the value at infinite time of this G is nothing but lambda 0 divided by 1 minus alpha, which is precisely the lambda bar that was defined in the lecture. So we recover this first result. And we also know how you decay to this particular stationary value. So you decay with a relaxation time that is of the form beta times 1 minus alpha, which is also related to the comments in the lecture. So you see that as soon as you have alpha, which is smaller than 1, everything is fine. As you approach this critical value of alpha being equal to 1, you have two divergences. So you have one divergence of the stationary rate in here, and you also have the divergence of this relaxation time. And this tells you that you are approaching a regime for this point process, which is unstable. And indeed, if you choose alpha larger than 1, the process is non-stationary. It is not well defined if you want, and you see it from the fact that you have an intensity which explodes exponentially over time. So if you have time to look at the homework 5, there is a simple code or a code to implement this Hawkes process with the exponential kernel, and you can play around with this parameter alpha, and you can really see what happens if you choose alpha becoming closer and closer to 1. So you see that the number of events starts increasing in a way that is somehow uncontrolled, as you expect from here. Okay, so this was the first point. Now, let me do another comment, which is good for the next exercise. So we solved, let me go back to the equation where it is. I erased it. So we had an equation for g of t, which was this convolution. So g of t is a constant. I know it's up there. Okay. So you see, it's a constant plus this convolution between the kernel and the constant and the function itself. And we are saying that we want to choose a kernel that is exponential. And we can solve the equation by Laplace transform, and this is what you should do for any arbitrary kernel. But if you have a kernel that is exponential, you can immediately guess what is the form of your function g of t, that is, by the way, this form in here. That is, you can guess that the function is itself an exponential. And this is because if you look at the right-hand side, you have an integral of phi, which is an exponential function. And if you assume that g is itself an exponential function, the integral of the product of two exponentials will give you back another exponential. So by adjusting the coefficient, you can match the right-hand side to the left-hand side and see that any exponential ansatz is a good solution for the equation up there. So this was another possible way to proceed, and this is what we are using now to solve another equation that is the point 2 of the exercise. That is now the equation. Yes.
I have a question about the solution we just found. So does this mean if we choose alpha equals to 1? Oh, sorry. Can you hear me?
Yes, it's always bad, but so far, yes.
Okay, sorry. If we choose alpha equals to 1, does that mean that we reduce the problem back to a Poisson process?
In here, you should, no, actually, it's the limit alpha going to 0 that gives you the Poisson process. So the question is somehow for which alpha I go back to a Poisson process. And the idea is that the limit of the Poisson process is given by having no memory kernel, if you want, in your process. So what happens in a Poisson process is that the probability to have a certain number of events in a given small interval is independent with respect to the previous history of the process, so to the number of events that you had before reaching that interval. And this is something that you would recover setting alpha equal to 0 in here, so killing this memory term that that carries memory about the previous realization of the process. And indeed, in the Poisson case, you just have that the rate that controls whether you have an event or not in a small interval T is a constant rate. So this would be Poisson. And now that we are going to compute this, we will be able to check that indeed the ratio, the clustering ratio of the Poisson process, which is equal to 1, is recovered for alpha equal to 0. Is it fine?
Yes, thank you very much.
Okay. So let's do that. And to do that, we have to, let's say, accept another equation, which is another integral equation, this time for the correlation function. That I am not deriving in here, but I think you find some derivation in the lecture notes, in the last chapter that was given of the lecture notes. And this equation has a name. It is called, there's a name that I forgot. So let me, where is it? Yule-Walker equation. Okay. And it is quite similar to the equation we had for G. So the idea is that you get the correlation between the number of events in two times, if you want, separated by a time shift tau. This is equal to alpha divided by G infinity. So G infinity, maybe I didn't define it, but it is simply the limit of what we just computed at large times. So for the exponential kernel, it was just lambda 0, 1 minus alpha. So this was lambda bar in the lecture. So this is what appears in here. Then you have your kernel. I'm rewriting equation 8, if you're looking at it today. And then we have another convolution again between your kernel and the correlation function itself. And this correlation function is assumed to be symmetric with respect to this time difference tau. Okay, now what we can do, so why we want to compute this? Because as you see from the today, there is an equation which relates our clustering ratio that is naturally related to a correlation function, because you see that it has 2 times appearing when you compute this variance. So there is an explicit equation which relates this quantity to this correlation function. So what we are going to do is to compute this and then use the result again for the exponential kernels to get the clustering ratio. And we can proceed exactly as before. So we can do the Laplace transform of this equation and solve it. And this is what you find in the lecture notes. Or we can use this idea that I just mentioned, that if phi is an exponential, then we should expect some sort of exponential form also for the function c. So it is consistent to assume, and this is what I'm going to do in here, that our c of tau has an exponential form. So it is some constant, capital C, times e to the minus some exponent that we have to determine, that I call gamma in here. And then I put an absolute value of tau, and I put an absolute value because I want to preserve symmetry of the correlation function. Okay, so this is an ansatz. So what I can do is I take this ansatz and I plug it into our equations, and then I use the equation to determine what is the expression for C and what is the expression for gamma. So the left-hand side is easy. So I get C e to the minus gamma. So now let's assume that tau is positive. So I have C e to the minus gamma tau. Then on the right-hand side, I have my exponential kernel, beta e to the minus beta tau. And then I have this convolution to compute. So this is the integral from 0 to infinity in du, alpha beta e to the minus beta u, which is my phi of u. And then C, and C is what? Is capital C e to the minus gamma. And now here I have to keep the absolute value because as you see, I'm integrating over u from 0 to infinity. So this can be both larger or smaller with respect to tau. So I have to split these two cases. So let's split these two cases. This is just a bit of algebra. So I have alpha beta over g infinity e to the minus beta tau plus alpha beta capital C. And then I assume first, so I do first the integration from 0 to tau, which I assume to be positive. So if I integrate from 0 to tau, I have e to the minus beta u. And then u is smaller than tau, so this is positive. So this is minus gamma tau plus gamma u. Okay. And then in the remaining part of the domain from tau to infinity, I still have e to the minus beta u, and then I have to flip the sign. So this gives me minus gamma u plus gamma tau. Okay. Now where shall I go? Maybe on the other side. Now I have to do simple exponential integrals over u. So this will be equal to, so this is the same as this, alpha beta over g infinity to the minus beta u, no, tau, plus so from here, what do I get? So I have a factor of e to the minus gamma tau that I can bring outside the integral. And then I have the integral of e to the minus beta, between brackets, beta minus gamma times u, which gives me, well, let me write it compactly. This will be 1 minus e to the minus beta minus gamma tau divided by beta minus gamma, plus, then I have the second term. Let me write it here. Sorry if there is a little bit of confusion with the space. So now in this case, I have to take out a factor of e to the gamma tau. And then I have the integral of e to the minus, this time between brackets, beta plus gamma times u, between infinity and tau. So this will give me e to the minus beta plus gamma tau divided by beta plus gamma, hopefully. Okay. And so let me now collect all of the terms which have the same exponential in front. So there are some terms which have a factor of e to the minus beta tau in front. So we have one here. This is just alpha beta divided by g infinity. And then you see that if I multiply this times this, the factor of gamma cancels, and I just get the factor of e to the minus beta tau. So this will contribute with minus alpha beta c divided by beta minus gamma. And the same from here. So this is plus alpha beta c divided by beta plus gamma. And then I have a unique term which depends at the exponent only on gamma, which is the term that I get from this product. So then I'm left with alpha beta c divided by beta minus gamma e to the minus gamma tau. Okay. And I'm rewriting this in this way because now you see that I have an expression on the right-hand side that I have to match with what we had on the left-hand side. And on the left-hand side, we only had the dependence on gamma. So what this means is that I have to kill the factor which depends on e to the minus gamma tau. So I have to set to 0 what is in parentheses in here. And this will give me an equation for C if I solve this. And then I have to match the prefactor in here with the prefactor that I have on the left-hand side, which is just the constant C. And this immediately tells me that I need alpha beta divided by beta minus gamma to be equal to 1. Okay, so from here, I can read that gamma, similarly to the decay that we had above, must be equal to beta times 1 minus alpha. And then plugging this expression from gamma in here and setting this to 0, I get out an expression for C that I will directly give you in a minute. And you can do it by yourself. So with this matching condition, I recover the full correlation function for the exponential kernel. So what I get is that my C of tau is of the following form. So now I use the expression that you can derive for the constant C, which is alpha beta over 2. There is 2 minus alpha divided 1 minus alpha, 1 over G infinity, that we know what it is. So this is lambda 0 divided by 1 minus alpha. So you can plug it in if you want. And then I have e to the minus beta 1 minus alpha times absolute value of tau. So above, I assume that tau was positive. If you assume it negative, you get a very similar result that gives you this final expression. Okay, and now finally, and perhaps I'm not doing this explicitly, but once we have the correlation, we can plug this expression into the form or the equation for rho, so the clustering ratio. So this requires doing other exponential integrals, but those are straightforward. So I will just comment on what you get in the end. So from equation 5 in the TD, where rho is called R, you know that this will be 1 plus 2 this G infinity integral from 0 to tau in du, 1 minus u over tau times the function C that we just determined. So C is an exponential, so if you integrate, this term will give you an exponential, and the second integral is just an exponential times u. So the fastest way to do this, if you have the integral of x e to the minus alpha x, is to write it as minus the derivative over a or alpha of the integral of e to the minus ax. So you just have to compute exponential integrals and then eventually derive it with respect to the exponent. So you can do this in here, and you get out the following that now we can comment. So we have a factor of 1 over 1 minus alpha squared. And then we have a factor that depends, that contains 1 over tau, which comes from here. Some numbers, 2 minus alpha over alpha. So these are coming from the constant C in the correlation function. Okay. And then we have exponentials coming from the integrals with this gamma exponent that is beta times 1 minus alpha. Okay, so again, what you see, so now this is an expression for arbitrary times tau. So what we can do is to study the two limits of this expression. So first we assume, so we have a relaxation time in here. Let me call it tau relaxation, that is 1 over beta times 1 minus alpha. So this tells me that if I choose times which are small with respect to these relaxation times, I can approximate this function roughly by, I can do the linear expansion of the exponential, and if instead I'm looking at very large times, I can approximate the exponential with 0 essentially, and this will give me the two limits. So for short times, meaning shorter than the relaxation times, I expand linearly this exponential, and what I get is that rho of tau is approximately, well, the same factor of 1 over 1 minus alpha squared. And then I have, so let me copy this, so minus alpha 2 minus alpha 1 minus alpha cube. And then you see, if I expand this, this will give me 1 minus tau, which cancels. So the 1 will cancel, and the tau coming from the linear term will cancel with this. There is a factor of beta that will cancel with this, and then there is a factor of 1 minus alpha that will cancel with one of these powers. So if you do this, you just get this. And you see that what you have in the numerator is 1 minus 2 alpha plus alpha squared. So this is precisely 1 minus alpha to the power 2. So you see that in this short time limit, your clustering ratio is essentially equal to 1. In particular, in the limit tau going to 0, this is, well, no, you have this singularity. Yes, in the limit tau equal to 0, this is exactly equal to 1 because you cancel this singularity with this linear expansion. And what is 1? Well, what is 1 is the Poisson ratio. And why do you get the Poisson ratio? Well, one way to understand it intuitively, so remember that we said that our lambda was lambda 0, that is what you would get if you just had a Poisson process, plus your kernel. And your kernel was an integral over times. And so what you can expect is that in order for this kernel to be important, you have to allow your process to run a little bit, because the process has to realize that there are some events at previous times and has to be excited by these previous events. And therefore, if you just look at very short times, you basically don't see the effect of this excitation kernel, and you just recover the Poisson result. On the other hand, if you go to very long time or large times, then you can eliminate this exponential. You also have a factor of 1 over tau that kills completely this second term on the right. And so you see that your rho of tau goes asymptotically as 1 over 1 minus alpha squared, which is what was given in the lecture today, and which is larger than 1 because alpha is positive, so the denominator is smaller than 1. So again, just to have an example in the homework, if you really do the simulation of the Hawkes process, you can compute this clustering ratio, and you do this taking the ratio of the variance with respect to the expectation value. And as a function of tau, you should see this, you can see in the solution, something like this. So you see that at 0 time, it starts from 1, and then it converges to some value that now we know it has to be equal to 1 minus alpha to the power 2. So you can choose a value of alpha, and then you can check that this is the case, and this is homework 5.4. I think. Okay. What else? Well, maybe just one final comment, which is related to the third point of exercise 1 that we are not doing in detail, but I will just comment. So in the end, what do we derive? So we derive, in particular, this expression for the relaxation time and for the asymptotic average rate, which is lambda 0, 1 minus alpha. And I just want to point out that you really see the effect of these excitation kernels. So on one end, you see the effect because whenever alpha, so when alpha is equal to 0, you recover Poisson. Whenever alpha is different from 0, you have a value of G which is larger. So you have more events than what you would expect in an independent Poisson process. And this is because as soon as you have one event, your excitation kernels promotes new events in your process. And this is what you read out from this. And also you have a relaxation time, which is again larger than what you would have in absence of the kernel. So when alpha is equal to 0, because so if you or actually this is larger than what you would have somehow if you just so this beta is what controls the decay of the kernel here, right? So this was the kernel times G of tau itself. So we have a natural scale at which this kernel decays, which is 1 over beta in our exponential example. And this tells you that if you have a mother event, so one point which occurs, then this will influence the future history up to times which are of the order of 1 over beta, naively. But then the fact that you have this self-excitation, it tells you that actually the influence goes over to times which are larger than 1 over beta by a factor of 1 times 1 over 1 minus alpha. And this is again an effect of self-excitation. So what happens is that you have a mother event. This, of course, will influence all the history in the future. But if the mother event gives rise to one son, so think again in terms of these Galton-Watson birth processes, the son itself will influence the future and will increase the probability to have more events. And this is what is measured by this factor of 1 over 1 minus alpha. And in particular, in the third part of the exercise, if you think about this as a birth and death, actually birth process, what you realize is that 1 over beta is like the fertility of the mother, so time scale over which the mother can make sons. But this is increased by a factor of 1 over 1 minus alpha, which is the average size of the family generated by the mother. And this accounts for the fact that the mother can generate many sons, and each of these sons will increase the probability to have future events. And this is what eventually will increase, if you want, the influence of the mother event by this factor of 1 over 1 minus alpha. So to make this a bit more precise, you can go and have a look at the third exercise. But somehow the idea is what I just sketched. Okay, so this was for what concerns Hawkes. And now we don't have much time. I just wanted, so for those of you who want to stay, maybe to sketch very briefly this idea of Fokker-Planck with multiplicative noise. So if you had time to go back to the TD3 and the solutions, you have seen how to derive Fokker-Planck, for instance, in the case of additive noise, and I think this is also discussed in other courses. So the only thing I wanted to point out is that whenever you have multiplicative noise, again, you have to always specify the prescription of discretization that you use. So whether it's Ito or Stratonovich, and you get 2 two different forms, if you remember, of the Fokker-Planck equation. So now this is, let's say, Fokker-Planck. I'll try to be short and just to give the main ideas. So Fokker-Planck came from Langevin. So in one dimension, you have dx over dt equal to some drift term, f of t plus our noise. And remember that we could discretize these equations. So we can say that over a small interval dt, the increment, so the value of the process at time t plus dt, is related to the value at time t by this f evaluated at some point within, let me call it x bar of t. Of course, this is an x. These are functions of the process. So this was a point to be chosen properly inside the interval t plus dt. And then we have the same times the noise in the interval times dt. And remember that the noise is of order 1 over square root of dt. So what we have in here is of order square root of dt. So we can rewrite it, and this is useful to derive the Fokker-Planck as, so we can call this as its scale. Sorry, now the d is, I call it capital D. Assuming that then I will take the limit delta t going to 0. So this is of order capital dt. So I can rewrite it as the order of magnitude, which is square root of dt, times some random variable, which is of order 1, and which is Gaussian, and which reproduces the statistics of the white noise, which means essentially that zeta square has to be equal to sigma square, where sigma is the variance of the noise at equal time. So if you want, Z is the little bit of noise which acts in the interval t plus dt, rescaled by square root of dt. Okay, and now this is essentially what you need to inject or a useful way to think about the problem when you want to derive differential equations like the Fokker-Planck equation. So the Fokker-Planck equation is an equation for a quantity p of xt given x0 t0. So what is this? This is the probability now averaged over all possible trajectories, so over all possible realizations of the noise, to be at x at time t, given that at time t0 I was in a given position at 0. And if you remember, the structure of the equation for this p was different depending on whether one used the Ito or the Stratonovich convention. So let me give you the form for Stratonovich. So we had to introduce this d of x is just sigma squared over 2 times g of x, which is the function which multiplies the noise in the Langevin equation. And then for Stratonovich, the form of the equation was as follows. So now I will drop the dependence on the argument. It was of the form dp over dt equals to minus the derivative over x of f, which is the function appearing in the Langevin equation times p, plus the derivative over x of d of x times the derivative over x of d times t. So there was, for Stratonovich, there is this symmetric structure that appears in the second derivative, whereas if you derive the Fokker-Planck for Ito, if you remember, you just have a double derivative in here of d squared times p. It's a square root, I think. No, this should be fine. Yes. Okay. Okay. And now, so given that we have not much time, I would just perhaps tell you the starting point or the main ideas of the derivation. So how do you derive an equation for this? So you can start from one identity, which is in general true for probabilities. That is that if you ask what is the probability to be at the point x at time t plus dt, given that you were at x0 at time t0, what you can do is to take any time between t0 and t plus dt and write that this is equal to the probability that you were at a given value of y at that time. So being at, let me write it directly and then recommend. So the probability that you reach x at time t plus dt, given that you were at y at the previous time t. And then you have the probability that you were at y at time t, given that you were at x0 at time t0. And you have to integrate over all possible conditions or positions that you reach at time t. So this is a very general identity of conditional probabilities, if you want. And then once you have this identity, what you do is you take both the right and the left hand side. You choose a function f, arbitrary and smooth. You multiply both the right and the left hand side by this function f, and then you integrate over x. So on the left hand side, the left hand side is trivial. You just have the integral over dx of f of x times p of x t plus dt, given that you were at x0 at time t0. And on the right hand side, you have a double integral. Right. And what you can do in this double integral is, so let me write it in the following way. So, or just to be short. So you have a double integral where you have to integrate f of x in dx. And now f of x, you assume it to be smooth. So this means that you can approximate f of x as f of y. So assuming that y is the point where you are at the previous time and the time difference between the times associated to x and the one associated to y is small, then you can expand this f, and you can write this as f prime of y times x minus y plus the second derivative evaluated at y over 2 times x minus y squared and so on. So now what I do in the left-hand side is to do the integration over dx f of x, and then I replace f of x with the expansion around y, and I will get different terms. So let me write the first one. So let me exchange the integration of y and x. So let me take first this first contribution, which depends on y. So I will have integral over dy of f of y. Then I have this second probability, which depends on your y. So I will put it here. And now I will drop the dependence on the previous condition on x0 and t0. And then in this case, I just have the integral over x of this. So p of x t plus dt, given that I was at y at time t. Then I have the term which contains the first derivative of the function f. So I will have integral over dy of f prime of y, p of yt. And now inside the integral, depending on x, I have an extra term because you see that I have this x minus y, so this increment which depends on x. So let me write it here. P of x t plus dt yt. Okay. Plus, I will have a term containing the second derivative, which is also important, and then I have higher order terms. So now let me introduce three quantities, and then I will leave you. So the first quantity, the three quantities correspond to the integrals over x, which I find at each order in the expansion. So the order 0, if you see, is just the integral of this probability. So this tells you what is the probability that you start at y at times t, and you end up somewhere at times t plus dt. Well, if you integrate over the final state, this probability is simply equal to 1, because you know that you will end up somewhere at arbitrary time, and if you impose no conditions, that the probability has to be equal to 1. This quantity here, instead, it is not equal to 1. It depends on y, and I will call it I1 of y. And you will have an analogous term coming from the second order expansion. So in the end, the important things that you have to compute, and with this maybe I will stop, are I1 and I2. So I1 is what I just defined. So this is the integral of a small increment with respect to the probability of your process. Capital small dt over y. So this is an average increment. So you assume that you start at y and you ask what is the average increment that I do over a small interval dt. And what is also important that will appear in the second order term is, as you imagine, the fluctuations of this increments that are just obtained taking the power 2. Okay. And now this is what you have to compute, and this is where, to compute this quantity, is where you have to be careful about the discretization. So we will probably go back to this, but let me just comment. So all of this details in TD 3, exercise 3. And if you do the calculation properly, assuming Ito versus Stratonovich, what you should find is that this term, I2, is actually the same for both Ito and Stratonovich. And it's easy to compute. Whereas this average increment is what is tricky. So this is what will take different form depending on the type of discretization that you choose. So this is what you have to be careful about, in particular if you do the Stratonovich prescription. And this is what, in the end, will give you two different forms of your Fokker-Planck equation, depending on how you choose to discretize your process. So I don't think we have time, no need, to go through this, but you can check it in the today. And if there are questions, as I say, there will be the 7 where we are going to discuss an example of this, and there we can go back to the details if there are doubts. Okay, so I think we can stop if there are no questions. Then I wish you a happy holiday week, and we will see each other in 3 weeks, I think. And I will write an email with all the information on the schedule. Okay.
Thank you.
Bye.
Everybody.
Thank you.
Thank you very much. Bye.